Trigonometry is all about relationships between angles and distances. So before we can start talking about trigonometry, first we have to agree on how we're going to measure angles. There are a couple good ways to measure angles. So one way you're probably already familiar with, let me draw a circle here. One way to measure angles is to break up a full circle into 360 little pieces. And then to measure an angle, you just count out how many pieces are there inside this angle. So here's 0 pieces, 1 pieces, 2 pieces, and so on, and you just count them up, and you might get up to, say, 50 pieces. And so this angle would have size 50. And we call this system of measurement, where there's 360 pieces in one full turn of the circle, we call this measurement system degrees. So we'd say that this is this angle is 50 degrees. That's an okay system to use, and we will use that system some of the time, but it turns out that mathematically it's actually pretty inconvenient. Part of the reason that it's inconvenient is because it's arbitrary. Why 360? There's no good mathematical reason for that. Another reason why it's mathematically inconvenient is because it doesn't actually relate angles and distances in any meaningful way. So we're going to also use another system of measuring angles, and this system is called radians. And here's how you measure an angle in radians. So let me put an angle in here. So to measure an angle in radians, first you measure two distances. The first distance you measure is the radius of the circle. We'll call that r. And the second distance that you measure is the length along this circle that the angle cuts out. And we'll call this distance s. S is, for some reason, the traditional letter for arc length. So the length along the circle is called the arc length, and it's abbreviated S. And then the measure of the angle is the arc length divided by the radius. And this unit, this way of measuring angles, is called radians. So we'd say S over R radians. Now you're probably asking yourself, why did we have to choose a circle to measure an angle? It seems like it's just as arbitrary as degrees if you have to introduce this arbitrary circle. But in fact, we'll see that the radius of the circle that you use to measure this angle doesn't really matter. So by taking this ratio, we really are measuring something about the angle and not just the circle that we used. So let's do a quick example. For example, let's figure out how many radians are in a full circle, are in a full turn. Okay, so that would be an angle that looks like this. All right, so to measure the number of radians in this angle, we would draw any circle centered on that angle. Then we need to measure the radius of this circle. Just to choose some circle, let's say that this is 2 inches in this circle. And now we need to measure the arc length for this circle. Well, since this is a full circle, the arc length that we're talking about is just the circumference of the circle. And you might remember that the circumference of a circle is 2 times pi times the radius of the circle. So in this case, that's 2 times pi times the radius is also 2, and so that's 4 pi. Okay, so the size of this angle, or the measurement of this angle, is the arc length, S, which is 4 pi, divided by the radius of the circle, which is 2. And this gives us 2 pi. All right. So a full turn in radians is 2 pi radians. So if we had chosen a different radius, how would this change? Well, if we changed this radius to, say, 3, what would that change? That would change our radius over here in our arc length. That would change to a 3. And that means that this arc length wouldn't be 4 pi, it would be 6 pi. So we'd have 6 pi over 3, and we'd still have 2 radians. You can see that no matter what radius circle you use to measure this angle, you always get 2 pi radians. So this measurement of 2 pi radians in the circle is really measuring something about the angle and not just the circle. As a bonus for knowing how many radians are in a full turn, now we have a conversion factor between degrees and radians. So a full turn is 360 degrees, but now we know that a full turn is 2 pi radians. So 360 degrees is equal to 2 pi radians. You can actually divide both sides by 2, and you get the slightly simpler conversion factor that 180 degrees is equal to pi radians. It's good to have a conversion factor like this because in some situations degrees are a little bit easier to work with, and in other situations radians are a little easier to work with. So we'll need to be able to convert between the two systems of measurement. So let's use this conversion factor on a couple examples. So for our first example, let's figure out what is 30 degrees in radians. So 30 degrees. Now remember, we have this conversion factor, 180 degrees is equal to pi radians. Now how I like to use conversion factors is I like to rearrange them to make one side of this equation equal to 1. You'll see why in a second. Since we want to get rid of degrees and produce radians, let's divide both sides of this by 180 degrees. We find that 1 is equal to pi radians over 180 degrees. So to convert 30 degrees to radians, we don't actually want to change what this angle is, we just want to change the units. Since we don't want to change what this angle is, really the only thing we can do to it is multiply it by 1. But we now know that 1 is actually equal to pi radians over 180 degrees. And this gives us some arithmetic that we can do, or we can simplify this expression. So first of all, the degree unit in the numerator cancels the degree unit in the denominator. We get 30 over 180. Well, we can cancel a factor of 10 by canceling the 0 there. And then 3 over 18 times pi radians. And 3 over 18, that's 1 over 6. So 1 over 6 times pi radians, or just pi over 6 radians. So 30 degrees is actually pi over 6 radians. All right, let's look at another example. Just like we can use this conversion factor to go from degrees to radians, we can also go from radians to degrees. So let's figure out what is pi over 3 radians in degrees. So pi over 3 radians. So again, we're going to accomplish this by multiplying by 1, but we're going to write 1 as a ratio of our conversion factors. We want to get rid of radians, so we are going to, since our radian unit starts in the numerator, we need to have a radian unit in the denominator to cancel it. Also, we want to produce degrees in the numerator, so we need a degree unit in the numerator. And now we just have to put numbers here and here so that this fraction is equal to 1. In other words, we have to put two angles in the numerator and denominator that are actually the same. And we know that 180 degrees is the same as pi radians. And now we can simplify this expression. So this radian unit cancels that radian unit. This pi up here simplifies away with that pi down there. And we get 180 degrees over 3, and that's 60 degrees. So you can see any angle measurement in radians you can convert to degrees and vice versa. There are actually a few angles in radians and degrees that you should know. Let me make a quick chart of them. So angles measured in degrees and angles measured in radians. So first of all, 0 degrees is 0 radians. That's no big surprise. The next one is 30 degrees, which we just figured out is pi over 6 radians. The next one is 45 degrees. Right, that's 45 degrees splits a right angle like this. If you work through the same process to convert this to radians, you get pi over 4 radians. 60 degrees. And actually, we did this one too. We got pi over 3 radians. You should know 90 degrees. That's a right angle. 90 degrees is pi over 2 radians. 180 degrees, that's a half turn. That's pi radians. And then, of course, 360 degrees is 2 pi radians. That's the very first one that we figured out. All right. So it seems like at this point, we've just made our lives more complicated by introducing a new system of measurement. Why not just use degrees all the time? Well, it turns out that using radians is convenient in situations where geometry is a factor, because radians are defined in terms of geometric quantities. So let's see how that can be useful. So it turns out that the Earth is roughly spherical, and the distance from the North Pole to the equator is about 6,220 miles. Let's use this to find the radius of the Earth. So since the Earth is, roughly speaking, a sphere, if you look at it from the side, it looks something like this. And the North Pole is up here. And the equator is around the middle. So there. And this distance along the surface of the Earth from the North Pole down to the equator, that's 6,220. Let's see, we should also draw the radius on this picture somewhere. So the radius of the Earth is right there. And we don't know it yet, so I'll call it R for radius. Okay. Well, let's see. It looks like right here, if we add this vertical line from the center of the Earth up to the North Pole, there's a right angle right there. And we know that right angle is pi over 2 radians. But an angle measurement in radians is an arc length divided by a radius. So we have pi over 2 radians equals, well, the arc length in this equation is this green arc length. The arc length in the definition of radians is the arc length along the circle cut out by the angle. And that's the green arc length, so that's 6,220 divided by, that's miles, divided by the radius, which we don't know yet. So now we can just do a little algebra. Let's see, multiply both sides by r. That gives us pi over 2 radians times r equals, on the right-hand side, the r's simplify away, and we're just left with 6,220 miles. Okay, and now we can multiply both sides by 2 over pi radians. Oops, I need it like this. 2 over pi. And on the left-hand side, these cancel. And on the right-hand side, let's see, we get 6,220 times 2 divided by pi. So let me work that out. 6,220 times 2 divided by pi. We get 3,959 and a bit. So about 3,960 miles for the radius of the Earth, which isn't exactly right, but actually it's pretty close. So you can see, since the radian angle measure brings geometry into it from the very beginning, it actually turns out to be useful in a lot of situations where degree measurements wouldn't really be helpful.